Question 4a. Ammonia reacts with the hydrochloric acid to produce the ammonium chloride, as shown in this equation. Draw a diagram to show ionic, covalent, coordinate bonding in the formula units of ammonium chloride. So you just need to draw one formula unit of the ammonium chloride, and for this one you no need to draw the dot cross. You just need to show the type of bondings. For the ammonium, you need to draw the three normal covalent bond between the nitrogens and hydrogen, and another dative bond between the nitrogens and this hydrogen. So this is the covalent bond and the dative bond. After that, you need to show the ionic. So you just put a bracket, square bracket for the ammonium and put the charge positive there. And its counter ion is chloride. So you just put the chloride here. So this is the ionic bond. Part B. An exothermic reaction occurs when ammonium is added to hydroxide. Identify the type of reaction. So for the reactions between ammonium and hydroxide, so it's something like this. When the ammonium and hydroxides react, it will form ammonia and H2O. So in this reaction, we know that the ammonium is the proton donor. So it's released one proton. So the ammonium now is acid. Hydroxide is the one that gains the proton. After that is formed H2O. So it's a proton acceptor. So we say that this is a base. So the reactions between the acid and base now is quite clear. We know the type of reaction. So it's an acid-base reaction. Part 2. Construct an ionic equations for this. So I already told you just now. So it's just this one. Ammonium with hydroxide form ammonia and H2O. Part C. Substitution reactions of the ammonia and hydroxide with a halogenoalkane both involve lone pair of electron. Part 1. Name the role of ammonia and hydroxide in this reaction. So because ammonia and hydroxide they have lone pair and is electron rich, so we say that these two species, they are nucleophile. So nucleophile is always a species with lone pair or with more electrons, right? So which can donate to others, especially electrophile. Okay, so part 2, suggest which species, ammonia or hydroxide, is more reactive during this reaction. Explain your answer. So the reaction is refer to substitutions reaction. Okay, I give you one example. Let's say now we have the chloromethane. So the chloromethane will more likely to react with hydroxide because hydroxide is charged negative. And of course, hydroxide and ammonia, they have the lone pair. The difference between hydroxide and ammonia is the charge. So because the hydroxide is charged negative, so it's easily get attracted to this carbon which is partial positive, and they can react. So therefore, if we want to compare the ammonia and hydroxide, hydroxide is more likely to react. So that's the standard answer. If let's say we put ammonia, ammonia still can react. It just is neutral, right? So the reactivity might not as great as the hydroxide, right? So that's why the answer in mark scheme is this one. So hydroxide is more reactive and is negatively charged, which is more attracted to the halogenal alkane, or you can say is more attracted to the partial positive carbon. So this is a mechanism when it's involved the hydroxide. So the lone pair on this oxygen, so it will donate or it will attack this partial positive carbon, and it will form this intermediate. So the CCl bond will break, and these two electrons will move to the chlorine to form chloride, and it will form the methanol. Okay, part D. When 2-bromo-2-methylpropane reacts with hydroxide, two mechanisms SN1 and SN2 both will occur. The SN2 mechanism is slower rate. Okay, so why SN2 slower rate? Okay, first we need to refer to the structure of this halogenal alkane. 2-bromo-2-methylpropane. Let's say this is the first carbon, second carbon, third carbon. So on the second carbon, they are methyl and bromine. So this is the 2-bromo-2-methylpropane. And this halogenal alkane is tertiary halogenal alkane, because the C with the bromine now is bonded to 3 alkyl group, so it's tertiary. Tertiary halogenal alkane will more likely to undergo SN1 mechanism. That's why SN2 is not really going to happen. That's why it's slower rate. And for this question is asking, sketch a graph on this figure 4.1 to show the reaction pathway for the SN2 mechanism. Okay, so before we discuss SN2, let's look at this 4.1, the two peaks here. So from this diagram, we know that this one, the one with two peaks, is SN1. SN1. So SN1 is involved two steps, like this. So this is a first step. So the first step is the bond breaking of this CBr bond. And after that, it will form this carbocation. So the second step is the hydroxide will attack this carbocation. So this is second step. So that's why for the SN1 mechanism, SN1, okay, for the SN1 mechanism, it has two steps. So that's why here you will see two peaks here. So for the SN2 mechanism, it's only involve one step. So SN2 mechanism only involve one step. One step, only one peak. And because it's already mentioned, it's slower. It's happen at a slower rate, means it's harder to happen. So why is harder to happen? Because the activation energy is higher. So therefore, you need to draw one peak, because it's one step, from the reactant to the products, and it must be larger EA than the SN1 mechanism. So again, this one with one peak is the SN2 mechanism. Okay, this is SN2 mechanism. And the one with two peaks here is the SN1 mechanism. Right, so you must draw one peak with higher EA compared to these two peaks. That's how you draw this figure in this figure 4.1. E1. Complete figure 4.2 to show the mechanism for SN1 reaction that occurs when this halogenal alkane reacts with the ammonia to produce these products. Include the charged dipole, lone pair of electrons, and the curly arrows. So first, we need to follow the question, because already mentioned is SN1. So we must make sure the CBr bond break in this step. So first you need to draw you need to put the dipole, partial negative on bromine, partial positive on carbon, and you must draw one arrow from CBr bond, and the arrow must point to the bromine. It shows that these electrons move to the bromine and it will form bromide. After this bond break, it will form this carbocation. And this carbocation will attack by the ammonia, because it said reacts with ammonia. So you need to draw one ammonia molecule, must show the lone pair on nitrogen. So draw one arrow from the lone pair, point to this carbocation. And it will form this intermediate. And you need to show the bond break. So one of the NH bond break, and this arrow must draw from the NH bond and point to the nitrogen to show that the lone pair will reform on the nitrogen. So means later the H plus will released, and the H plus will combine with the bromide just now to form the HBr. Part 2. Identify inorganic product that's formed in the reactions in figure 4.2 just now. As I told you just now, after the reaction, after the mechanism, it will produce the hydrogen bromide, HBr, and the HBr will react with the ammonia, because one of the reactants is ammonia. So therefore, the inorganic product that produce, it will be the ammonium bromide. So the HBr with the ammonia to form this ammonium bromide. Okay, part 3. Give the systematic name for the organic products. Okay, this one. So the structure is something like this. Let's put the carbon number. So this is the first carbon, second carbon, third carbon, and fourth carbon. And the NH2 is bonded to second carbon. We will choose the nearest branch, right? So means this is going to be second carbon, not third carbon. Okay, after that, we can name this compound. When the NH2 with the hydrocarbon, so the functional group we call amine. Because it's 4 carbon, so it's butane 2 amine. Because this group, this NH2 is bonded to second carbon, so that's why it's 2 amine. So it's butane 2 amine. F part 1. Complete table 4.1 by drawing the structural formula for the intermediate that form when 2-bromo-2-methylpropane reacts in SN1 reaction. This is the one that I told you just now. Here. So this is 2-bromo-2-methylpropane reacts with this SN1 mechanism. So this is the intermediate that produced. So you just put this structure into the table. Okay, so this is the one. The carbocation with 3 methyl group. So this one is the tertiary carbocation, and this is secondary carbocation. So tertiary carbocation is more stable than secondary. Okay, so now last part, identify the halogenal alkene in table 4.1, these two, that has a greater tendency to react using SN1 mechanism. So if the carbocation is more stable, so if you undergo SN1 mechanism, so we will choose the tertiary carbocation here. So this one. So because tertiary carbocation is more stable as compared to this secondary, so means the 2-bromo-2-methylpropane will undergo, or more likely undergo, SN1 mechanism. So this is the first understanding that you must have. Based on the types of the carbocation, then we see which one will undergo SN1 mechanism. So once you identify this, okay, 2-bromo-2-methylpropane, then you need to explain. So because the 2-bromo-2-methylpropane, it will form tertiary carbocation, this one. And this tertiary carbocation is more stable. Why is more stable? Because the carbocation is bonded to 3 alkyl group. And this 3 alkyl group has a positive inductive effect. So what is positive inductive effect? Because the alkyl group has electron donating nature, so it will push its electrons towards the positive side, which is the carbocation now. And when the electron is get near to this positive side, so this positive side is lesser, means is more stable. So this is the stability means. So when the charge positive is getting lesser because of the positive inductive effect of this alkyl group, so it become more stable. Right? That's the meaning. That's the meaning of positive inductive effect. Okay. So that's all. Thank you.